All right. Okay, today we're going to be going over the physics homework for Ken's class. Um, we're going to start with some equations. Let's see, just got to figure out. Yeah, let's go with like purple. Um, yeah. So, first things first, we're going to start with circular motion over here. Just going through our equations so we know all what we're going to need to use. For distance and circular motion, since everything's going in a perfect circle, we just need the circumference of the circle. That'll be the distance. So that will be 2 pi times the radius, 2 pi r. Amazing handwriting, but yeah. So velocity for circular motion, velocity is always distance over time. In this case, the distance we travel, we just covered, is 2 pi r divided by time. This will generally be in seconds, so our units, unless otherwise stated, will be in meters per second. Forgot to cover that for distance. That will generally be in meters. So, centripetal force. This is the force acting on an object moving in a circle, which we'll talk more about this later, but that's always going to be pointing towards the center of the circle. But centripetal force we'll write as F sub c, or force centripetal, and that's going to equal mass times our velocity squared divided by the radius. So force is always mass times acceleration. This part isn't as important, but we got our mass. Acceleration of centripetal force is v squared divided by r. So slap those two together, we got this thing. Force of gravity, gone over this a little bit, but force of gravity, F sub g, is just going to be mass times the acceleration of gravity. And for this one, we're always assuming we're on the surface of the Earth when we use that. So we can go 9.8 times mass. Forgot to do the units for these. For centripetal force, since it's a force, it's always in newtons. Same with the force of gravity, going to be in newtons. All right, so that's our equations there. I have a document typed up with all the stuff in it that probably looks a little better than this. So universal gravity. For the force of gravity between two objects, this is where we get like varied gravity, and we're not using the other force of gravity. This will be F, hold up, F, okay, loading in, F of big G. I use big G for like variable gravity, little g for normal gravity. That's going to be our gravitational constant, which I'll talk about in just a second, times the mass of object 1 times the mass of object 2 divided by radius squared. Okay, gravitational constant, that is always going to be 6.67 times 10 to the negative 11th. So whenever you see big G, plug that in. Or if you want to just write this equation with the 6.67 in it, that works. Radius, it's a little different from a circle, although that's sometimes what we'll talk about. That's from the center. This might be better to type out, but we're not doing it. Center of each object. Now, important note on this, that's only important if we're dealing with like planets. There's one question in this that's comparing the distance between two fruits. We don't really need to know the small distance from the edge of that fruit to the center. But when we're dealing with planets, like sometimes we'll have things orbiting around a planet. We need to know Like if it gives us the radius of that planet, that's only to the edge of that planet. Then we need to know how far above that it's orbiting. So draw a little thing. If we got a planet, something orbiting out here, radius only goes to the edge. We then need to add on this distance. We'll get more practice with that, but that's just a little brief thing. So the acceleration of gravity, this isn't explicitly given in the packet, but it's good to go over. That's going to be A sub g, acceleration of gravity, is the gravitational constant, which we have right up here, times the mass of the object that is like pulling on the other object. So if it's asking like if someone's skydiving, and it's like what is the acceleration of gravity they experience, we'll want to use the mass of the Earth for that one. It's the thing that's kind of causing the gravity on the object. Divided by radius squared again. This looks really similar to this for a reason. In the packet, they assume that you can figure out, using our gravity equation over here, the force of gravity an object experiences is equal to like the universal one. So we can plug in mass of the object, which we'll say is m2 times a, equals gravitational constant times mass of like the Earth in this thing. We'll say m2 is the skydiver from the last problem, times mass of object 2 over radius squared. And because we'll say a sub g, because we have an m2 on this side and this side, they cancel out, giving us our normal like acceleration of gravity we just went over. That's really complicated. Just use that formula. Okay, sweet. So on to problem 1. All right, let me just get my pen back up here. Purple. Okay, so for this problem, I don't know why it gives us these numbers. We don't use them at all. It's basically, this car is driving in a circle. It's going that way around. You can see that there. It's kind of hard to see. So basically, what we know, this car can turn in a circle because it has friction. In this problem, it's saying if it suddenly became frictionless, like what direction would it go in? Basically, it's asking us to find the velocity vector, we can sort of think of this as if this car suddenly stopped turning and just went straight, what direction would it go in? Would it go towards A, B, C, or D? In this case, it would just go straight towards A. So that'll be our answer for this one. If at any point you have questions, you can always reach out to me or any other support person. Okay, question 2. Car moves along a curved track. What is the direction of the normal force of the driver when the car reaches the lowest point down here? So, we are going to draw a free body diagram. That's the thing with the square. I drew that very poorly. Where we draw the arrows for each of the forces. So when it's at the bottom here, we'll have 3 forces. We'll have the normal force, gravity, and centripetal force, since this is a curved track. That one's not as important here. Okay. I fed you misinformation during the equations. Centripetal force always points out from the curve, acceleration goes in. Confusing. Yeah. So anyways, on our free body diagram, we'll have gravity pulling down. We'll have our centripetal force. Since that goes out from where we're at, this will also be pulling down. And the normal force. That is basically, essentially it's saying like, if we push on a table or something, that table is also pushing back on us. It's basically the reason this car doesn't just fly through the ground. So normal force has to counteract those. So that's going to be pushing up, which is our answer there. So on to question 3. Now we got to do number crunching. Okay, so a 120 kilogram pilot, that's important. Whenever it gives us numbers in problems like these, we should pay attention to them, is doing a vertical loop with a radius of 677 meters at 170 meters per second. Okay, that's given values. Let's start with part A. With what force does the seat press against him at the bottom of the loop? So down here, we're looking for basically the normal force. So we'll want to start with part A with our free body diagram. It's going to be our square again. So at the bottom here, we'll have gravity pulling down. Since he's going in a circle, we'll have our centripetal force. And remember, that pulls away from the center of the circle. So in this case, if he's at the bottom, that will also be pulling straight down. So we'll have our force centripetal. And since this plane is not flying down towards the ground, we got to have something counteracting these. And in that case, that is going to be our normal force. So the force that counteracts things sometimes will change. If it's like you're swinging a ball on a rope, that's going to be tension in the rope. We'll go over that if we run into it, but here it's a normal force. So since this question is essentially asking us to find the normal force, which is the seat pushing against the pilot would keep him from falling down, that would give us our normal force. In this case, we can see our force of gravity and our centripetal force are pulling down. Normal force is the only thing pulling up. So our normal force is going to be the force of gravity plus the centripetal force. And that's going to be our normal force. So we're going to start with the force of gravity. This one's pretty simple. If you remember, this is just mass times 9.8. Don't need to do like the universal acceleration. We can just use 9.8 here. So if we plug that in, we just get 120, we know is the mass of the pilot up here. We go 120 times 9.8. And that's going to give us, let me just plug this in the calculator, 1176 newtons. Yay! That's our force of gravity. Okay. Yeah, basically, whenever you're on a final answer, just remember to put the units. In intermediate steps like this, don't need to worry about it. Okay, so now that we have our force of gravity, let's find our centripetal force. If we go back to our equations, remember that is mass times velocity squared over the radius. Luckily, we are given all of these values, which is really nice. So we can plug in our mass, which is 120 kilograms, times our velocity, which is given up here, 170 meters per second. So that'll be times 170 squared. I just like putting it in parentheses to say, hey, this is a separate thing. We plugged it in there. Divided by our radius, which is 677 meters. So if we plug this in a calculator, we're going to want to do our squared first, the multiply by 120 second, and then divide that number that we get from these by 677 third. You could also plug it in a calculator, kind of like this. And remember this fraction thing, that's dividing. So throw that in our calculator quick. So 170 squared is that. Hold up, I got kind of a weird calculator. This might take a second. 70 squared. times 120 divided by 677. I'm using Desmos on my phone because I don't actually have a graphing calculator with me. Okay, so we get this long string of decimals. Since our first three decimal places are 5.99, I'm going to round that up to 0.6. So we should get 5,122.6 newtons. Yeah. So now that we have our centripetal force and our force of gravity, we can add those up. So 5,122.6 plus 1,176 equals, let's find that out. Hold up. Okay. Desmos is not being fun right now. So 5,122.6 times 1,176. That should give us, oh wow, times, not wanting to do times. Okay, plus 1,176. Should give us about 6,298.6 newtons. And this will be our normal force, because we found out that just adding them together gives us our normal force. So that's part A. Now, on to part B. What is the minimum speed the pilot can take the vertical loop without falling off the seat at the top of the loop? So this is basically saying, well, actually, okay. So at the top here, again, we'd only have the possibility of these three forces acting on them because we're not worried about small things like air resistance or anything. So we'd have gravity pulling down, and we'd have centripetal force going out again, which in this case is up. In this case, we're not going to have normal force. So it's saying the minimum speed he can take the loop without falling off the seat. That is going to be when gravity and centripetal force are exactly equal, which means there will be no normal force. So if you were in this plane, you would feel weightless, like nothing is pulling on you at just that one point. So we want to figure out where force of gravity equals centripetal force. Luckily, force of gravity is going to be the same in this equation, which we found right over here. So we want to figure out when the centripetal force is 1176. I'm also just going to hop down here for the next step. And I'm going to switch pen colors for this, just to differentiate a little bit. Okay, so we want to figure out when 1176 is our centripetal force. Here, I'm going to plug in our centripetal force equation on this side. So we'll get 1176 equals, and our centripetal force equation, mass times velocity squared over r. So in this case, remember, we're trying to find the minimum speed, so we don't know v. This is what we're trying to figure out. Luckily, the mass and the radius are still the same. So let's plug those in for our next step. Oh, sorry. Eraser. Okay, and then is this what I want? That's not what I want. What am I doing? Okay, so mass is 120 kilograms again, times velocity squared divided by 677. So, yeah, again, we're trying to solve for v, which means we want v all by itself with nothing else there. So we want to get all these other numbers and that little squared up there over to this side. So first things first, whenever we got stuff in a fraction, we want to get rid of that. We don't like that. So remember, we talked earlier that this fraction thing means it's dividing. So currently, this whole side is being divided by 677. To undo division, we use multiplication. And because this is algebra, got to do the same thing to both sides. So multiply both sides by 677. If we multiply this by 677, we'd have a 677 on top, which would cancel out both of those. So let's put 1176 times 677 in our calculator. If you can do that in your head, I commend you, but that is hard. Okay, so we get about 796,152 equals, and then because the 677 is canceled out, we are just left with 120 times v squared. Okay, so now from here, that 120 is kind of getting in the way. That's going to be our next step. This 120 is multiplying our v squared. So to undo multiplication, we do division. We're going to divide both sides by 120. I'm going to go back up here. Okay, so we want to divide our 796,152 by 120. Hold on, how can I... divided by 120. Okay, so if we divide that 796,152 by 120, we get 6. Oh, hold up. Okay, I'm going to give myself a little more room up here. So we're going to bring it back up here. So we get 6,634.6 equals, since this 120 cancels out, just v squared. Awesome. Okay, last step. Well, first, okay, I'm just going to switch the sides of the equation. I just like having the variable on the left. Doesn't matter what way we write it, but I prefer this. So that thing is being squared right now. To undo squares, we do square roots. I drew that horribly, but we're going to square root both sides. So we'll be left with v equals square root of 6,634.6. That should give us about 81 point. I'm going to go to the third decimal, 453. Awesome. All right. Okay. I would like you to pause and take a second, if I don't know, and find the units. So units, meters per second. Yeah. So this is our answer to part B. That is a minimum speed he can take, because that value, when plugged into our centripetal force equation, will give us 1,176. All right. Okay, on to the next one. Wow, that's zoomed out. Okay. Question 4. All right, let me get my marker back. Go back to purple. Okay, two objects with masses m1 and m2 are originally a distance of r apart. If we think back to our equations quick, there's only one that includes m1, m2, and r. That's our universal gravitation equation. This one's kind of weird because it doesn't give us any specific values for these. Yeah. So then the magnitude of gravitational force between them is F. We'll just generally use F. The masses are changed to 2m1, 2m2, and the distance is changed to 4r. What is the new magnitude of the gravitational force? Okay, so basically we're going to be comparing the force of gravity in the beginning, which is our constant, times m1 times m2 divided by r squared. So we have this equation originally, then they change. We're going to say they change by a factor of x. So hold on, I'm just going to rewrite this. So we have x times our original equation remember x is going to be our factor of change. That's going to be over r squared. Okay. The reason we have this factor of change is because now we can set this equal to our new one with 2m1. So we double both masses. I just messed up. Draw on that. Okay. Times 2m2 over, and now we plug in 4r where r was. So we're gonna have 4r and then square that. Okay. So the reason we put this x in here is because we're gonna change this equation by some unknown amount. We're gonna figure that out, and then we're gonna end up with our doubled masses and our quadrupled radius. So basically, this is a whole lot of canceling out variables. Oh, and this side is also multiplied by g. I always forget that, by the big G. So when it comes to things like this, if we have the same variables in the same spots on both sides, we can kind of cancel those out. Since both sides are being multiplied by g, we can cancel those out. Bam. Okay, and then we have this whole mess here. We have an m1 and an m1 on both sides, so we can cancel those out. This does not get rid of the 2. The 2 will stay there. We have an m2 and an m2 on both sides. Cancel those out. Oh, and these both were on the top of the fraction, so we know we're good to go there. That 2 will stay. Okay, I just realized I skipped a step. So this 4r squared, if we actually square that out, that's going to be, remember, squaring something is multiplying it by itself. So 4r times 4r is going to give us 16r squared. So if we rewrite the bottom there as 16r squared, we see that we have an r squared on the bottom here and an r squared on the bottom here. So we can cancel out our r squared. That 16 will stay. So we've gotten rid of all of our variables so far. So let's rewrite that in a much cleaner fashion without all these canceled out things. So all that's left on this side is x, our factor of change. And that's going to equal 2 times 2, because we canceled out the m1 and the m2, but both the 2 stayed, and they're still multiplying, divided by 16. Canceled out that g, all the other variables, so this is all we're left with. So this is how we're figuring out what we're changing this by, which will help us get our answer. So x, if we multiply those 2's out, will equal 4 over 16. This isn't really an option in any of our answers, but we can simplify this fraction a little bit. If there's a couple different ways to do this, we can figure out how many times 4 goes into 16. We can put it in a calculator, divide those out, get 0.25. Either way, we can simplify this fraction to 1 over 4 is our factor of change. And this factor of change is applying to our original force of F. I just completely covered that up. So we'd have 1/4 F, which would equal F over 4. That will be our answer, so B. Okay, on to the next one. Oh, hold up. Question 5. Nice. All right. So as a rocket moves away from the Earth's surface, the rocket weight does what? Does it increase, decrease, stay the same, or depend on how fast it's moving? So for this problem, we want to focus on what weight is. Weight, Actually, hold on. I'm just gonna type this out. I can't keep writing like this. Okay, so weight is the effect of gravity on something's mass. So sweet. Okay, now we can go back to our marker. Yeah. So it's the effect gravity has on something's mass. So to change the weight of something, we either have to change the force of gravity acting on it or its mass. So if we think about this rocket moving away from Earth, it's going way out here, a little rocket ship. Beautiful drawing. As it moves away, let's think about mass first. Its mass would technically be decreasing a little bit because it'd be burning all that fuel behind it, getting a little lighter. That's not really what this question is focusing on, so we're going to say mass stays the same for all intents and purposes. Now, does gravity change? If you think about just going out in space or anything, we could think about this through our equation. I think that's harder. The farther we get away from a planet, the weaker the gravity is. So, if gravity goes down, that means its weight is going to go down too. Mass stays the same, but if we think of weight as like our force of gravity equaling mass times acceleration, which we can kind of think of the acceleration of gravity. If gravity gets weaker, this number gets smaller, which means our force of gravity gets smaller. So, the weight would decrease. If that explanation seemed kind of weird, that's fine. Basically, farther away you get from a planet, weaker the gravity, which means gravity has less of an effect on something's mass, meaning its weight is lower. Yeah. All right, question 6. Ooh, yay, acceleration of gravity. Okay, so if we have a mass of 96 kilograms, this is completely irrelevant, and climb on top of Mount Everest will be about 8,851.3 meters above sea level. That's important. What is the acceleration due to gravity at this altitude? Given this is the mass of the Earth, it just looks like me equals that much. That's saying mass of Earth. And then RE is saying radius of Earth. So we see that it's asking for the acceleration of gravity. So we know we're going to need our acceleration of gravity equation, which is our big G times the mass of the object giving us the gravity, which in this case will be Earth, divided by the radius squared. So we know big G, we know the mass of the Earth, because that's given here. We need to figure out the radius. Although the radius of the Earth is given, we're this far above sea level. So we need to add the radius of the Earth to our height. So we can put this in a calculator. We can put in 6.38. That's going to come back in a second. There we go. Times 10 to the 6th. We want to put that in parentheses so that comes out as one number. And then plus 8851.3. And this will give us, let's see. Just got to type this in quick. Times 10 to the 6th. Plus 8851.3. Okay, that's a big number. We get about 63888 51.3. Okay, big number. But this will be our total radius, and that's in meters. away from the Earth. That's how far we are from the center of the Earth, which is where that gravity is starting from. That's, yeah. So, now that we have our radius, we also have our mass, we know g. Let's plug in all our values. So first things first, big G. That's 6.67 times 10 to the negative 11th times mass of the Earth, which is 5.97 times 10 to the 24th. Divided by our radius, which is that really long number. Sweet. So, first things first, let's get rid of this fraction. We can put this in a calculator. Put that top thing in parentheses, divide it by our radius there. Before I put that in the calculator, I'm just going to get ready to write this out again. So we'll still have g. We're not messing with that yet. Times 10 to the negative 11th. That'll be times whatever we get from this. Now let's put that in our calculator. So we get 5.97 times 10 to the 24th divided by our radius. Okay, that will give us a long string of decimals. Yours might show up a little bit different. It might, so there's two forms this might show up in. It might show up as a long string of numbers like this. It might show up as like 9.34 E17. E means 10 to this power. So this would be translated to 9.34 times 10 to the 17th. This is what I got. So I got 9 point, hold up. Okay, we're just gonna go 3, 4. I'm gonna go to the third decimal place times 10 to the 17th. Well, there is technically a rule for how many decimal places you should go to. We are not worried about that. I just generally like going to the second or third every time, unless it rounds up to something really nicely. But in this case, we're just going with the 9.344. So now we have these two. Doop, doop. We're going to multiply our big G into this thing. And we're going to see what we get. All right. Okay, so get that number times 6.67 times 10 to the negative 11th. Okay, sweet. So I got another long string of, wait, what? That can't be right. Okay, I see what we did. Hold on. You may have realized I already made this mistake. Okay, so backing it up. I was like, holy, our acceleration of gravity should not be this big, and it shouldn't, and that's because we've got to plug in this value, 6388851.3, and we got to square it. I forgot to square it. Oh my gosh. Okay, so backing it up. I'm gonna go back up here, and we're gonna go squared. Okay, so luckily I was able to change that pretty quickly, which is nice. So this value, if we follow the formula correctly, which I did not, we should end up with, I apologize for that. Okay. Should end up with 1.4 6, I'm just going to round it there, times 10 to the 11th. Okay, this looks much more correct. So now we're going to multiply this to g. So that answer times 6.67 times 10 to the negative 11th. Okay, awesome. There we go. That's a much more reasonable answer. So should hopefully get around 9.75. It should be like 0.7556. I'm going to round that up to 0.756. Awesome. So I didn't leave enough space there, but our units will be in meters per second squared. Yeah. So notice how our normal acceleration of gravity is 9.8 meters per second squared. Here we have just under that because we are a little farther away from sea level. Okay. There we go. That's right. Okay, question 7. All right. Just get my marker set up. So in one hand you hold a 0.12 kilogram apple. In the other hand you hold a 0.2 kilogram orange. The apple and orange are separated by 0.75 meters. What is the magnitude of the acceleration of gravity that the orange exerts on the apple and the apple exerts on the orange? So for this, let's start with part A. Gonna need our acceleration of gravity equation, which is g times mass of the object providing the gravity divided by radius squared. Don't forget that squared. That's a silly mistake. Hold on. Okay. So in part A, we're looking for the acceleration of gravity that the orange exerts on the apple. So in this case, the mass we'll be using is the oranges, since we're looking for like the gravity the orange is putting on the apple. We're also given our radius, and we know g. So let's plug those in. Get our big G, 6.67 times 10 to the negative 11th. I'm going to have to write on the orange here, times our mass of the orange, which is 0.2, divided by our radius squared, 0.75 squared. Okay, so let's figure out this fraction first. I'm just gonna write this with our G still there. Oh, okay, there's a 10 in there, I promise. Okay, so now in our calculator, if you don't know how to put this in, we're gonna do this squared first. That's gonna be our first step. And then we're going to divide the 0.2 by the answer we got for that squared as our second step. So hopefully in the end, we should end up with, oh, hold up. Okay, just got to type this in. Sweet. So hopefully we should end up with 0.3 and then 5's repeating after that. So I'm going to go 0.356. Just round it up. So yeah, now we got this. We got our G. Let's just multiply those together. See what we get. So 6.67 times 10 to the negative 11th times our previous answer should give us about 2.37 times 10 to the negative 11th. Yeah, that should be our answer for this, and this will be in meters per second squared because we're dealing with acceleration. Sweet. That's part A. And for part B, we can pick a different color. Go red again. Okay. B. Now we're finding the force the apple exerts on the orange. These should be pretty similar answers, but not exactly the same. So, start with our acceleration of gravity equation again. M1 over r squared. Again, don't forget the squared. That's a silly mistake. So, let's plug in our values. This time, we're looking for the force, the acceleration the apple exerts on the orange. So, this time we are going to plug in the apple's mass because we're looking for how the apple affects the orange. So, we know our g value. Boop, boop, times 10 to the negative 11th. Shoop, times mass of our apple, which is 0.12, divided by the same radius squared. 0.75 meters squared. Okay, let's figure out this fraction first. Again, if you don't know how to type that in, we're just going to do our squared first, and then divide our 0.12 by that answer. So, I'm going to start by just moving our g down, times 10 to the negative 11th, times, and let's figure out that fraction. Divided by 0.75, oh, that's not what I was going for, 0.75 squared. So hopefully we should get around 0.21 and then 3's repeating. Or, yeah, but we're going to go with 0.213. Right, so then I'm just going to multiply this to our g. I forgot to mention this last time, but if you're plugging this in a calculator, make sure you put parentheses around your g. So it's like, okay, this is one thing we got to figure out, and then multiply that. Although I think in this case it doesn't matter. So we get 6.67 times 10 to the negative 11th times the answer we just got. It should give us around 1.4, a couple of 2's and then a 9, so we'll go 0.42 meters per second squared. And this should be our answer for part B. Okay, awesome. On to question 8. Oh, okay, question 8. Lovely, lovely question 8. So, this question, if you're watching this video, is likely optional for you. If you are not sure, check in with Ken, case manager, or any other person. Yeah, there's so many steps in this. I'm still going to go through it in this video. Yeah, it's very complicated. It's probably optional for you. Yeah, still going to walk through it. If you want to follow along, great. Otherwise, you can skip ahead in the video to when I start the next problem. But if you're sticking around, okay. Suppose that a man who has a mass of 86 kilograms is orbiting the Earth, which has a mass of that, at a distance of this many meters above the surface of the Earth. What is his period in hours? That's saying how long does it take him to go around the Earth in hours? And we're given the radius of the Earth here. Okay, so this one's long because we need to find f of big G and then set that equal to our centripetal force because he's staying even in orbit. And then using our centripetal force, we find velocity, and then using that, we find time, but that's in seconds, and then we find time in hours. That's basically the steps. A lot of steps, but we're going to walk through them quick. Actually, I'll keep that up. That might be helpful. And time in hours. Okay, so this is the general guideline we're following. So step 1, step 2, step 3, step 4, step 5. Okay, so step 1, we need to find the force of gravity between these two things. So we're going to use our big F of g equation. So big G times mass of object 1 times mass of object 2 divided by radius squared. Okay, luckily we know all of the values for this. Big G, 6.67 times 10 to the negative 11th. Mass of object 1, it doesn't matter whether we assign the Earth or the dude to object 1, but I'm just going to pick the dude. So 86 times, and then mass of object 2, that's our Earth. So that's going to be this value up here, which is 5.98. Didn't they use 97 in another problem? I don't know. Okay, that is the mass of our Earth divided by the radius squared. So our radius is going to be the center of the Earth to the core. That's what this value is. And then plus the distance from the edge of the Earth to our dude. I'm going to put this in one big parenthesis that we can just plug into calculator. So, big parenthesis. First things first, radius of the Earth, which we're going to put in a smaller parenthesis inside that. In your calculator, you can just do 2 sets of parentheses. Hold up. I can't see if that is a 6 or an 8 up there. That is a 6. Okay. Sweet. Times 10 to the 6th. Close that parenthesis. And then plus 4, 9, 8, 8, 9, 7. Sweet. If you're wondering why I did all these parentheses, basically when you put this into a calculator, if you want to do this all at once, you can put those in parentheses too. What this tells the calculator to do is, okay, start with the smallest parenthesis, we do that, and then we multiply that by this thing out here. For the bottom it says, okay, we're multiplying this out first, and then we're adding in this. So it's not like we're adding this to this, and then multiplying it by 10 to the 6th. That would be a mess. But okay. So f of g equals big G times 10 to the negative 11th. We're going to figure out the top first. Oh, and this is squared. Don't forget the squared. That's a silly mistake. So we'll put that in a calculator. So we got 5.98 times 10 to the 24th times 86. Okay, sweet. Gives us nice and pretty whole number. So, oh, and if you don't know how to type this into a calculator, do this first, and then multiply that second. So this should give us 5.1428 times 10 to the 26. You don't need to use all those decimals. I don't really know why I wrote them all out. Times 10 to the 26th. Okay, and then we're going to figure this out. So if you don't know how to plug this into your calculator, do this first, add that second, and then square it third. I'm going to rewrite that because that looks like you're putting it to the 23rd. Okay, so let's see. First steps first. We're going to do our 6.38 times 10 to the 6th. Shoop. Okay, now that we have that, we are then going to add that big number out there, plus 4,988,997. Awesome. Okay, we have that. So that should be in this parentheses. So this should come out to about 6,878,997. Then we're going to square that. Okay, that was horribly written, but okay. If we square that out on the bottom, we should get about 4.732, I'm rounding that one up, times 10 to the 13th. Okay, so next steps next. Hold on. Okay, we're gonna need some more room, so I'm gonna be erasing stuff as we go. If you're confused on how we got somewhere, feel free to back the video up. So then we're gonna move that up there. Awesome. Okay, back to our marker. Okay. Just getting rid of that one. Awesome. Okay, so now we're gonna divide out that fraction, this fraction. I'm just moving our big G down. Times 10 to the negative 11th. Okay. So let's see. First things first. We're gonna do 5.1428 times 10 to the 26th. Awesome. Once you get that, divide that by so if you don't know how to put this in your calculator, you can put it in with parentheses around both. Just do parentheses this divided by parentheses this. Or you can figure out this individually, and then divide both of those. I am going to be doing putting them in parentheses stuff. 4.732 times 10 to the 13th. And we should come out with about 1.09, I'm rounding that up, times 10 to the 13th. Okay, now that we have this, we are putting these together. All right. So I would put them both in parentheses, multiply them out. That's how I'm going to do it. So 6.67 times 10 to the negative 11th. All right. Times parentheses 1.09 times 10 to the 13th. Right? Yes. Okay. And that should give us 727 newtons. All right, we're done with part 1 of 5. This is why this question is optional. So, erasing this stuff. So, about 727.03 newtons. I'm just going to round up to 727. Select. Got that? Awesome. Okay. So now we need to set our force of gravity equal to centripetal force, because if we draw a free body diagram on this dude, gravity's pulling him that way. Centripetal force is pulling him that way. These two are even if he's in an orbit. So 727 equals our centripetal force equation, which is mass times velocity squared over r. So because we're using this equation to find velocity, which we use to find time, we're going to be solving for velocity. All right, actually, okay, here's what I'm going to do. Hold up. I'm going to write this in a different color. So 727 equals mass times velocity squared over r. So we know the mass of our dude. Because we're measuring the force on the dude, we're going to use his mass and his radius, which thankfully I have erased, so we'll be finding that again. I would back up for the steps. Again, that's just the radius of the Earth, plus how far above the Earth he is. Yeah. So 727 equals 86 for his mass times velocity squared, which we're solving for, divided by his radius, which I'm going to figure that out quick. The reason we're doing this radius again and not just to the edge of the Earth is because the center of the Earth would be the center point of his rotation. That's what he's rotating around. And the radius is the distance to him, which is both of those parts. So, see, I'm going to do 6.38 times 10 to the 6th in parentheses, and then plus our 4,98897 to get our 6878897. Yeah, this one isn't squared, so we're all good to go there. Now we need to solve for v. First step, multiplying this out. We're going to multiply both sides by our really long thing on the bottom, because that'll cancel it out in the fraction. So we're going to multiply that by that. So we take our 6878897, multiply that by 727, or vice versa. Doesn't matter which way we put it. This should give us about 5.00 times 10 to the 9th equals 86v squared. Next step, we're going to move it up here. Going to divide by 86. 86 is multiplying, division undoes that. So divide both sides by 86. You can see that. Okay. So we divide by 86. 86's cancel out. We just want to take that 5 times 10 to the 9th and divide it by 86. Okay, that's still a long string of numbers. All right, so that's 5. Mine is not rounding. Your calculator probably did. 675.8 equals v squared. Awesome. So that's being squared. To get rid of that, we square root everything. I'm also just going to switch the side the variable is on, so it doesn't matter which way we write it. Just want to make that clear though. So we get v equals the square root of that really long string of numbers, which should be about 7625.66. Woo, and that's in meters per second. So, hold up. Okay, now it's erasey time. That's our work. I only have so much space here, so I'm going to be erasing this. Oh my gosh. Okay, this video is much longer than I thought it would be, so I apologize. So that's our velocity. Now we're going to pick a new color. We'll go green. So for our next step, we use our velocity, which we know is distance over time, to solve for time. So we're just going to change this up quick to be 2 pi r, which is our distance, over time. And again, I erased our radius. Okay, so we know that our velocity is 7625.66 meters per second, and that is going to equal 2 pi times our radius, which again I have erased, and is that whole thing. So I'm going to just switch r out for that long parentheses of stuff, times 10 to the 6th plus 4,98897. Okay, over our time, which we're solving for. Okay, so first things first, we want to simplify that top. So, got 2 pi times that. Let's figure out our radius again first. So, we got 6.38 times 10 to the 6th plus 49889. Nope. 498897. Oh, wow, I was right. Okay. That's our radius. I'm just going to do this whole top in our calculator once we find our radius, which is at 6878897. We're going to multiply that by 2 pi. You should have a pi button on your calculator. If you can't find it or don't know or don't have it, you can approximate pi as 3.14. I wrote that abysmally, but so let's multiply that out. 2 pi times our previous answer gives us, oh my gosh, I don't like it giving us really long strings of numbers. So 4, 3, 2, 2, 1, 3, 8, 4.56 over time. Now we need to solve for time. I'm going to multiply both sides by t to get it out from the bottom of the fraction. So if I do both sides by t, this cancels out. We're just left with that number, and then we have our 76255.6 times t. Which I can write as 76256 or 0.66. Nice. Okay, there we go. Nailed it. And still on the eraser. Nice. Okay, 7625.66 equals. Oh. Silly me. Just oh my gosh. 25.66 t, because we just multiplied by t, equals that super long string of numbers. 4, 2, 2, 1, 3, 8, 4.56. All right, we can divide both sides by the 7625.66. So that will cancel out, and we'll be left with just t equals that really long string of numbers divided by 7625.66. Okay, and that should give us about 5,667.88 seconds. The problem here is that it's asking for his period in hours. We have it in seconds right now. So to convert to hours, we have our seconds. We know that there is 60 seconds in a minute, so we're going to divide by 60. And then we know that there's 60 minutes in an hour, so we're going to divide by 60 again. So seconds divided by 60 twice. We can also do divided by 3,600. That will give us the same thing. Since we're dividing by 60 twice, we multiply those 60s together, we get that. Yeah, time saver. So we divide our answer in seconds by that 3,600. Okay, 5,667.885 divided by 3,600 should give us 1.57 hours. That is our final answer, and oh my gosh, I'm glad to be done with that answer. Okay, awesome, good stuff. Okay, don't know what I'm doing. All right, question 9. Awesome. Okay, so the acceleration of gravity on the moon's surface is about 1/6 the acceleration of gravity on Earth. Given that the radius of the moon is 1/4 that of Earth, find the mass of the moon. So we're going to use our acceleration of gravity equation because that's what it's given us. Here's the radius of the Earth. So let's just set up our equation first, and then we'll worry about what we're plugging in. Acceleration of gravity equals that times mass of what's supplying the gravity, which is mass of the moon. That's what we're solving for, over radius squared. Sweet. So we know it's about 1/6 the acceleration of gravity on Earth. So that is 1/6 times 9.8. Or you can write that as 9.8 divided by 6. So that is our acceleration of gravity on the moon. If we, hold on. Okay, so first things first, we found that 1/6 acceleration of gravity. Oh, let's find that 1/4 radius. So it's 1/4 of the radius of the Earth. Luckily, we're given the radius of the Earth. So we can do our 6.38 times 10 to the 6th, which is our radius of the Earth, divided by 4. Hold on, let's see what those give us, actually. So I'm going to do that 9.8 divided by 6 first, because I didn't do that. So that's 1.63 repeating. That's just what that little dash means, but I don't actually need that dash, so we'll get rid of that. And then our radius. So we have, if you don't know how to do this in a calculator or anything, do this thing first, divide it by 4 second. All right, I'm just going to put it all in parentheses. It's 10 to the 6th. Divided by 4. Awesome. So this gives us about 1595000. Shout out to Desmos for never rounding anything in scientific notation. Long numbers. So now we have our radius and our acceleration of gravity, and we know g, so we can plug in everything and then just solve for mass. So our acceleration of gravity, if we plug that in, was that 1.63 repeating. So I'm just going to go 1.633 equals our big G, which we have, 6.67 times 10 to the negative 11th, times the mass of the moon. We don't know that. We're trying to figure that out. Divided by our radius squared. So that's 1595000 squared. Awesome. If you're wondering why I always put things in like variables in parentheses, that's just a habit. Okay, so basically we're just solving for m. Right now we've got m in a parenthesis. We don't like that. So we're going to multiply both sides by our radius squared, which is this value. I'm just going to put that in a calculator. Just do parentheses, that number, squared to both sides. This will cancel out the fraction there. So we just want to multiply this by our radius squared. Let's see, so 1.633 times our radius, which is that 1595000 squared. Okay, and we should get 4.154 times 10 to the 12th. Yeah, that's what we should get for that. Since this fraction cancels out, we're left with big G times mass of the moon. All right, so now all that we're left with is that big G over there. We divide both sides by that. 6.67 times 10 to the negative 11th. We should get a really big number. You'll bring that back up here. These will cancel out. We'll be left with just the mass of the moon on one side. And let's figure out our numbers. So We take that answer we just got, that 4.154 times 10 to the 12th. We're going to divide it by 6.67 times 10 to the negative 11th. All right. And that should give us about 6.228 times 10 to the 22nd kilograms. That should be our answer for this. Yeah, really big number. That's about right though. Okay, let's see. Question 10, last one. Okay, at a certain distance. Oh god, okay. Just completely zoomed all the way out. All right. A certain distance from the center of the Earth, a 4 kilogram object has a weight of 2 newtons. So we're going to want to know that it has. Why is that yellow? Ah. You know, I want to do red for this one. We're having fun. Okay, 4 kilograms with a weight of 2 newtons. Find the distance from the surface of the Earth. All right. So there's 2 ways we can go about this. We're given the mass of the Earth and the radius of the Earth. We're going to use our force of gravity equation. That's our big G times mass of object 1 times mass of object 2 over radius squared. Okay. So, we are trying to find its distance from the surface of the Earth, which is included in the radius. So we're just going to solve for radius first, and then we'll figure out the distance. That's what we're going to do here. I think that's a little simpler. So, first things first, force of gravity. We are given that it has a weight of 2 newtons. In that case, that is going to be our force of gravity. So that'll be 2 equals G, which is 6.67 times 10 to the negative 11th, times mass of object 1, we know that's 4 kilogram, times mass of object 2, which is the Earth. Oh, I was right. They did use 5.97 in another one. Woohoo. Times 10 to the 24th. Sweet. All right, divided by our radius squared. All right, so here's what we're going to do. We're going to multiply both sides by r squared first. Just get this r to the other side out of that fraction. So those will cancel out. We'll be left with 2r squared equals 6.67 times 10 to the negative 11th. I went kind of quick there. Since it's algebra, we can do the same thing to both sides, whatever it is. If we multiply this side by r squared, we just get 2r squared. If we multiply this side by it, we'd have an r squared on the top of our fraction here and one on the bottom. That's why those cancel out. Okay, and then we're left with this stuff. Since this is all multiplying, oh, that's 24, not 25. Okay, yeah. I'm just going to throw this all in a calculator. You can just put those all in a line, and we'll figure that out. All right. Desmos, don't fail me now. So 6.67 times 10 to the negative 11th times 4 times 5.97 times 10 to the 24th. Sweet. So our 2r squared is 1.59 times 10 to the 15th. Oh, not 15. That is incredibly wrong. Okay, so 1.59 times 10 to the 15th. Awesome. All right, now we need to get that r all by itself. So let's divide each side by 2. That'll cancel out. Be left with r squared equals so that previous number we just had divided by 2 should give us 7.96 times 10 to the 14th. Awesome. Then we square root both sides. We end up with r equals square root that last number we had. Yikes, that's rough. Okay. 282.20524.45. Okay. So this radius, this includes both how far it is from the Earth and the radius of the Earth. So to figure out so it includes from the center of the planet to the edge plus the distance to the object. So if we subtract the distance from the center of the Earth, we're left with just that distance from the surface of the Earth. So we do that number minus 6.38, that's a parenthesis, I promise. So 6.38 times 10 to the 6, I'm realizing red was a poor choice of color. So subtract that out. Take that really long string of numbers, subtract. If you don't know how to put this in your calculator, I would keep those in parentheses. Otherwise, figure that out first and then subtract it. 6.38 times 10 to the 6th, which is that right? Oh, that is right. Okay. Okay. So I'm gonna rewrite this. So it should, our radius or distance from the Earth, I'm just going to keep it as r, should be 2.184 times 10 to the 7th. Let me just double check that that's right. 2.184 times 10 to the 7th. Yeah, okay. We are all good there. Awesome. So that is its distance from the center of the Earth. Awesome. Gonna erase all this, get some more room to work. Hold up. I think there's an easier way to do this. Look at that. Look at that. I'm so smart. So then, that's our distance from the center of the Earth. We are picking a different color. Okay, if the object is released at this location, what is its initial acceleration? So, I'm going to use our acceleration of gravity equation. That equals big G times mass of the thing supplying the gravity, which in this case is Earth, that's supposed to be an E, divided by our radius squared. Okay, so I have in my calculator, I kept our total radius, which is what we need for this. That is 2.822 times 10 to the 7th meters. That's going to be our radius. We know the mass of the Earth, we know G. So let's plug those all in. G times, oh wow, okay. We do not plug it in by just writing the variable. Okay, so A acceleration of gravity equals 6.67 times 10 to the negative 11th times mass of Earth, 5.97 times 10 to the 24th, divided by our radius squared, which is this value, 2.822 times 10 to the 7th. All that is squared. Okay, let's do our fraction first. We're going to figure out our top, we're going to figure out our bottom. That's step 2. Then we're going to divide them. That's step 3. So move our big G down. Times. Okay. So we are going to have our 5.97, that's not a 4, I promise, divided by 2.822 times 10 to the 7th times 10 to the 7th close that parenthesis, square all that. Okay, should end up with 7 point, and round that up to 500 times 10 to the 9th. If we multiply these together, our acceleration of gravity. So 6.67 times 10 to the negative 11th. Okay. Times our previous answer should give us 0.500 meters per second squared. Woo. Okay. Yeah, thank you for watching. That is all of the questions. Finally, this was so much longer than I thought. If anything doesn't make sense, or if you ended up with different answers, just let me know. We'll work it out. But yeah, thank you for watching.